Welcome to Module 3, Lesson 2, more generating equivalent expressions. Okay, we will continue to stress the fact that addition and multiplication can be done in any order. That's the commutative property, and any grouping, the associative property. Okay, I think I might have said that wrong here or there, but not a real big deal. But again, commutative is any order, can move numbers around. Associative is any grouping, and that generally means when you're messing with the parentheses. Okay? This any order, any grouping idea, as we come to learn, can be applied to a subtraction problem by using the additive inverse relationships. And also it could be applied to a division problem using the multiplicative inverse relationships. And we'll talk more and more about that, because we know when it comes to commutative and associative properties, they only work with addition and multiplication. Therefore, to get them to work with subtraction and division, we need to turn the subtraction into addition and the division into multiplication. And we remember how division becomes multiplication, because all we need to do is to multiply by the reciprocal. Okay? So for example, I mean, we've always talked about that in terms of fractions, but I mean, just a basic number, you know, if we had 3, let's do something different. How about 6 divided by 2? This could be 6 times 1/2, because 1/2 is the reciprocal of 2. Okay, so yeah, this is how we could always change. I mean, any division problem can be expressed as a multiplication problem as well. Probably not something we thought of much in the past, but hopefully this becomes more and more clear to everyone as we move through grade 7 math. Okay, so let's go ahead and get started on this opening exercise here. Now in this opening exercise, it asks you to, kind of makes a statement first, of course. It says additive inverses have a sum of 0. Okay, additive inverses, okay, have a sum of 0. Fill in the center column of the table with the opposite of the given number or expression, then show the proof that they are opposites. Okay, and the first row here is completed for you. The expression is 1, the opposite of 1 is -1, and the proof of opposites, of course, we need to add these two values. So 1 plus a -1 equals 0. Okay. Now, if you would go ahead and do that for the rest, get as far as you can. I mean, it gets a little bit more and more complex, but you shouldn't have any trouble. Just apply what you know. Okay, so here we go. Let's go ahead and correct these. This opening classwork. Pretty simple up at the beginning. Opposite of 3 is -3, and then the way you prove it is just 3 plus -3 equals 0. Okay, writing a proof. Opposite of -7 is 7. -7 plus 7 equals 0. Opposite of -1/2 is +1/2. Add -1/2 plus a +1/2, you get 0. Opposite of x is a -x. Okay, and then if you add an x plus a -x, you're going to get 0, just like you would with any number. So you can see in this case that something good to know is that these variables, they are going to work similarly, or just exactly like any number would work. Okay, every variable has an opposite, which is either its opposite sign. Okay, now 3x, right, is a term. So the opposite of 3x is a -3x. Okay, it's not a -3 x, it's negative 3x, because here we have multiplication implied with the 3 and the x right butted next to each other. Proving that, we just add the 3x we had originally, and then we add the negative 3x. We're adding its inverse, and we get 0. A little more complex here, in that we have an addition or a sum here, x plus 3. Then we have to separate these out. Now we have a negative x plus a negative 3. Okay, and we'll go ahead and prove that. We put the original expression there, and then our opposite expression here. And now what we can do, because we have our properties, we can use the associative and the commutative properties to move things around. So if I take my x from this one here, and I take my negative x here, put those together here, and then my 3 from here, and then my negative 3 over here, put those together here, and we know, of course, that these opposites are going to add to 0, and then 0 plus 0 equals 0. That's my proof. And did a similar thing down here with the 3x minus 7. Okay, the opposite of this is a negative 3x, and now you're going to add a 7 plus 7. Okay, that's going to be added now because it was subtracted in the original expression. Okay, so we write that here. I just wrote it out 3x. I just changed this right away, 3x plus a negative 7 instead of 3x minus 7. Makes it more handy. And then negative 3x plus 7, which is the opposite of that original expression. Do the same as I did up here in this idea, using my associative and commutative properties. I've moved things around. So I put the two 3x's together, or the 3x and then the negative 3x, and I put the negative 7 and the 7 together, and both of those inverses are going to add up to 0 there, 0 there, therefore it totals out to 0. Now, one of the generalizations or a rule for the opposite of a sum, we've heard it before, and you've heard me say, and haven't been exactly totally clear about it, but this whole idea that the opposite of a sum is the sum of its opposites. Now, hopefully, that is becoming clearer and clearer to you here, because as you can see, here is my sum right here. If I do x plus 3, now the opposite of that sum is the sum of its opposites. Okay, so in this case, I have negative x is the opposite of x, and then negative 3 is the opposite of 3. Okay, so this sum that I've written, x plus 3, is the opposite of it is this, which is the sum of its opposites. Okay, and that would make sense down here as well. Here you had 3x, now we have negative 3, which is the opposite, and then we have had a negative 7, and we have a positive 7 here, which is its opposite. Okay, so the opposite of this sum is the sum of its opposites. Okay, and it works the other way around as well. Okay. Okay, now example 1 is asking you to subtract expressions. These problems are going to start looking a little bit, a little more and more confusing maybe, or a little more complex, but they truly don't have to be that much more complex if we just apply the rules and apply our new knowledge to all of this. Okay? So here there's a couple of ways to do this. One way I find a lot easier, okay, than the other, which would be this. If we follow order of operations here, and you remember our order of operations, and that was PEMDAS, if you remember that. PEMDAS, which says that we do parentheses first, and that's the part I want to talk about, okay? And this idea of parentheses, PEMDAS, this was exponents, multiplication, division, addition, subtraction, okay? And that was that idea of order of operations. When you have a long and complex expression, how do you go about solving it? Well, you start with parentheses. Okay, so if you follow this idea of order of operations, you could just do it this way. Do what's inside the parentheses. So if I do 40 plus 9, that's 49. And I do my 30 plus 2. I don't need to do that. 30 plus 2, that's 32. And then I subtract them both. Subtract one from the other, I get 17. Pretty easy, huh? Now if I did that step by step, I'd probably want to make it look like, well, let's just go ahead and do it more formally. So then I would have 49 minus 32, and then 17. Okay, would be my answer. All right? And that's using order of operations. Pretty darn easy in this case. Now, if I wanted to do the opposite of a sum is the sum of its opposites, which we talked about before, I would need to just go ahead and leave this 40 plus 9 alone. Okay, but now instead of subtracting it, I want to add its opposites. Okay, so the opposite of 30 plus 2. Okay, and this 40 plus 9, of course, is 49. Then I'm going to add, and the opposite of 30 plus 2, of course, still 30 plus 2 is going to be still 32, but now it's the opposite of them. That's why I have my negative sign. So now I have a negative 32. So 49 plus a negative 32 is 17. Okay? A little bit more complicated. It might help you later on to understand other problems a little bit better. So you could have done this either with this order of operations, doing the parenthetical stuff first, and then in this case we had parenthetical, and then all we had to do was subtract. Okay, you only used 2 of those. We didn't have any of the EMDA involved there. But with the opposite of a sum is the sum of its opposites, what we did is we went ahead and just took care of that by making it an addition problem, okay, and then adding. Okay, so in this case, order of operations might have been the way to go. So here's one where we have, the next one is B, is a problem where we have 2 different variables. As you can see, we have an X and we have a Y, okay? And of course we have just some numbers as well, okay? So let's take a look at how that's going to work. Okay, so it says subtract. We have 3x plus 5y minus 4 minus 4x plus 11. So you see we have two sums here, or 2 expressions right there and there, and we are going to subtract them. Okay, so hopefully you can see that we're trying to subtract this 4x plus 11 from the 3x plus 5y minus 4. Okay, sounds kind of weird, but truth is it's just like 10 minus 5 or whatever else. Okay, the best way to handle this one is not with order of operations, because the one up top here, we had no variables, okay? So in this case, the order of operations works out really, really nicely, really swell. But here we have some variables. We actually have, like I had said, two different variables. We have an x value, we have x variable, and we have a y variable. So with this one, let's just go ahead and do the subtraction as adding the opposite. So let's go ahead and do that. So we'll just keep our 3x plus 5y, okay, but now let's put a plus negative 4, okay, all of that, and then we are actually going to add, continue to add, and now we're going to do the opposite of 4x, so negative 4x plus 11, okay. All right, so just to show you what we have done so far. Okay, so we've kept this pretty much intact, except for over here when we had a negative sign here. We've made that, adding an opposite, adding the negative, okay, instead of just straight negative. On the other side, we have added this plus sign here, because we want to continue, we want to just add everything across, but we have done the opposite of the 4x plus 11. So we've taken what's inside of that parentheses there, the 4x plus 11, and we've just done the opposite of it, okay? Now we want to extend it out further, so each and every term is separated, okay? So we have terms here. We have 3x, we have 5y, we have negative 4, we have right here negative 4x, and then that's going to be a negative 11 actually, okay? So we're going to separate all of these out, all right? So let's bring them down. So now we have 3x, stays the same, nothing happens there. We're going to add 5y, okay? And now we have still our negative 4, okay? These are all looking good, at negative 4. And then we're going to add, now we have negative 4x, because whatever's inside of that parentheses there is negative because of our negative sign in front of it. Negative 4x plus negative 11. Okay, again, you have to remember that 11 is negative because of this negative sign here. Okay, because what we did is we took everything inside of that parentheses and turned it around opposite of, okay, because we had to account for the fact that we were doing subtraction at first, okay? So now what's really nice about this is we have every term separated, okay? Every term separated, and we're just summing, we're just adding all of these together, okay? So now what we have to do is we just combine our like terms, okay? So if we combine our like terms, we have 3x, and we're going to add that to a negative 4x, okay, which came from over here. Okay, see that one here? These are like, I guess I could maybe do this here. So here's these two are like terms, okay. Another like terms, well actually we'll just go ahead and do then we're just going to add the 5y, because that's the only y that's around, okay. And then we're going to add negative 4, and then add that to a negative 11. Okay, so we're keeping these nearby because these two are also like terms, okay, straight out numbers, all right? So we have like terms in the x's, like terms in the straight numbers, and then we have the y sitting by itself. So then what we do is we just take and we combine them. So 3x plus a negative 4x, of course, is negative x. Then we're going to add 5y, because there's nothing to combine it to. And then we are going to add negative 4 plus negative 11, of course, is a negative 15. Okay? Now, we no longer need that in parentheses anymore because we're not going to work with it. We've gotten to its simplest point. So our final answer would be negative x plus 5y minus 15. Okay? And keeping those in that order is generally the way we do it. We have, because x and y is going to be what we're going to be seeing mainly, okay? We have x first, followed by the y term, and then our number term, okay? So that order, x, y, number term, okay, that is going to become very, very familiar to you, keeping it in that order. Okay, well, let's go ahead and check the equivalency of these expressions. We subtracted out these two expressions here, and we came up with this. Now, what we want to check, is we want to prove, is that they are indeed equivalent, okay? And the way to do that, as you may know already, is to actually plug in a couple of values for a value for x and a value for y. Let's just go ahead and use the numbers 2. Let's say x equals 2, y equals 6. You guys are going to be doing a lot of this in the future. And again, something I find incredibly fun. So let's go ahead and plug in. If we plug in here, we have 3, and then we have times 2, plus 5 times 6, keep minus 4, then minus 4 times 2, plus 11 in there. Okay? So now that we have all, well, we soon will have all values, we can, we could just use our PEMDAS, our parentheses. But let's just go ahead and solve this here. So we have 3 times 2 is 6. And again, that 2 is coming from here, okay, because we're just plugging in 2 wherever we had x, okay? So that's 6 plus 30, because 5 times 6 is 30. And again, that 6 came from here, okay? Minus 4. Okay, then minus, and then 8. 4 times 2 is 8. Plus 11. Okay, so if we go ahead and do the parenthetical stuff, so we have 6 plus 30 is 36, minus 4 is 32. Okay, and then we subtract this, which is 8 plus 11, which is 19, and that would give us a total of 13. Okay. So by plugging in 2 for x and 6 for y, we came up with 13. That's what it evaluates to. And then if we take this more simple expression down here, and we just put this, so that's negative x is negative 2, because again, plugging in right here, okay? Negative 2 plus 5 times 6, and that's 6, of course, coming from here, okay? Minus 15. One more thing to do here. Negative 2 plus 30 minus 15. And yeah, so we have negative 2 plus negative 15 is negative 17. And then 30, take away 17, equals 13. And they do work, okay? So we have proven the equivalency, or the viability of our answer. What's really nice about the any order, any grouping idea is that it allows us to write sums and differences as vertical math problems, okay, vertically. And you're going to see this is going to be required at times as well. But yeah, a lot of fun, I think anyway, because we can move things around, because we're going to take, right now we're going to actually find the sum here of these two expressions by aligning the expressions vertically, okay, aligning them vertically, all right. And before we weren't doing that. Excuse me, what's up top here? We weren't doing that at all, okay. We were combining like terms, etc. But now we're going to do this all vertically, okay. And so what that means, firstly, is we're going to just mess with them first. Not mess with them, but we're going to actually create all separate terms, okay? We want each term to live on its own, okay, as we did up here. Remember, we got to this point, we had all terms separated, okay? So let's go ahead and do that. Do that right now, okay? So let's go ahead and work with this one. So we have 5a plus 3b plus negative 6c. Okay, so you see what I've done there. Just made that minus 6c. I've turned it into a plus negative 6c. Continuing plus, and then we have 2a plus negative 4b plus 13c. Okay? So again, this this negative 4b is exactly the same as this here. So if adding a negative is the same as subtracting a positive, okay? Just so you remember that. I haven't changed the value of anything here, okay? Again, just to further this, again, to separate them out, I now have all of these different separated terms, okay? They all live on their own, okay? And now what's nice about that is I can take my 5a, plus 3b plus negative 6c, all right? Put it on the top, and then I'm just going to add, okay, because I'm finding the sum. My other a value, which is 2a, see where that comes from over here, okay? And then plus, again, I'll do plus negative 4b. And you can see what I'm doing. I'm lining up, all the a's, all the a's here. They're my A, and then all my b's over here, my B and my B, and all my C's over here, my C, and I'm going to have another C right there, which is going to be plus 13C, okay? And then just like you would do any vertical addition, put a line right there, all right? And then we're going to go ahead and, work it like you would any addition problem, okay? It doesn't matter left to right, right to left when you're adding this way because you're not going to carry or do anything like that, okay? But just for old time's sake, we can start from the right as we would usually. So if I have a negative 6c and a positive 13c, I have a positive 7c. Okay, this is going to always stay plus here. And now if I have a positive 3b plus a negative 4b, that is a negative b, okay, negative 1b. You don't need to put, express it as a 1b because we don't really need the 1, okay? And then we have 5a plus 2a, okay? That's a solid 7a, okay? So now we have 7a plus negative b plus 7c. Again, to get to a place, our final answer, we take everything out of parentheses, okay? Therefore, we would write this as 7a minus b plus 7c, okay? And yeah, that's it. And again, keeping it in order, A, B, C, always helpful, okay? There we go. Again, hopefully this takes some time to understand. You may make a little mistake here and there with some simple addition, subtraction. Remember adding those negatives and positives together, and all those rules really important. But hopefully some of you find this as thrilling as I do. Okay, well, let's go ahead and do the next one. I was thinking maybe I could just let you guys do this one on your own. Just pause here. I'll pause and then go ahead and find the difference. Now we're talking difference. We were talking sum before, all right? And again, by doing it, lining the expressions vertically, okay? Really important, of course, now is that you are, doing 2x plus 3y minus 4 minus the 5x plus 2. So, this expression needs to be on top, okay? Needs to be on top because you're taking this away from that, okay? Very, very important because you can see now how we can't move that around. I mean, up here we were doing the sum we were doing the sum here on A, okay? You could have, flip-flopped these if you wanted to because it's adding, okay? It was the addition. But we can't do that here, so very, very important. You're always going to put, and it's probably just as a general rule, this is always going to, if you're going to do things vertically, this expression is always going to go on top, and this expression here is always going to go on the bottom, okay? So, give that a whirl, see how far you can get, and come on back and check it here. Okay, let's see how you did. I just went ahead. The first thing I did was try to get all of these terms as sums and get them all out. So I have 2x, 3y, negative 4, negative 5x, negative 2. Okay, these are the numbers I'm going to use. And again, here's my one expression. Here's my other expression. Okay, And again, that left expression always needs, so we're talking about a difference, needs to go on top. So we're going to do 2x plus 3y plus negative 4. Okay, so now we have subtraction sign. Okay, and then we have negative 5x and plus, there's nothing here, because there's a 0 as a placeholder, plus negative 2. Okay? All right, so here's where things can become a little bit confusing, okay? Because now we are finding differences. We always need to know that we are finding differences. Okay, and the confusion comes with this right here, okay, with this negative sign, because you're thinking we're going to subtract because we're taking the difference. But what we have done is we don't actually use the subtraction sign, okay? What we do is we actually assume addition here, because what we've done in this step right here is we have created a sum, and you can see that right there, okay? We have changed everything, so all subtraction has been converted, changed into addition, all right? So therefore, you're going to add, what you're actually doing is combining, okay? A better word than and find the difference, find the sum, is just to combine, okay, when you combine, all right? So right here, if we just do this one at a time, we have, and again, we can start, right to left. Negative 4 plus negative 2 is negative 6, okay, and let's just keep these separate like that for now, okay? And then we have 3y plus 0, of course, is just simply 3y, okay? And then we have 2x, a positive 2x, and a negative 5x, which is going to give us a negative 3x, okay? And then for our final, we just take away any of our, we no longer have a need for parentheses, so it's going to be negative 3x plus 3y minus 6, okay? And that would be our final answer right there, okay, for this one, okay? And again, just to reiterate, just to repeat why, even though we were finding a difference here, why we actually used a plus sign here was because in this step right here, when we used the additive inverses, or the opposite of the sum of the opposites is the opposite of the sums, sum of its opposites, we put that together and we made these just a series of sums, okay? Sum, adding, oh, don't want to do that, it's messy. We made a series of sums, therefore we could go ahead and add both of those expressions, or, like I said, a much better word to use is combine. Okay, and like this curriculum is so very diligent about, we are now going to apply some of what we're using. And for example, here in example 3, we're going to use expressions to solve problems. Okay, because truly in life, that is what we are always trying to do, solve a problem. Everything we do is pretty much around solving problems. All right? And so here's the statement here. A stick is X meters long. A string is 4 times as long as the stick. Express the length of the string in terms of X. Okay, and this is something we actually had done probably prior to this. We've actually done this. We actually did this at the end of Module 2. Okay, so if we know the length of a stick in meters is x, okay, we have x meters is the length of that stick, and that is right here. All right. Then, if we know that the string is 4 times as long as the stick, then that length of the string is going to equal 4 times x, okay, or 4x meters long, okay, 4x meters long. All right, so 4x. The length of the stick in meters is x. The length of the string in meters is 4x because it is 4 times as long, okay? And the x is just a variable. It doesn't stand for times. It's just a variable because it relates to the length of the stick, okay? But the 4 is the multiplier because it is string is 4 times the length of the stick, okay? Now to move on to B, if the total length of the string, and now we're talking about plugging in, actually having real values, if the total length of the string and the stick is 15 meters long, how long is the string? Okay, so this is going to take a little bit of work. Okay, so I would like you to try this one. This is similar to one of our end of module assessment problems that did give people a problem. Make it work. You have what you need right here. Okay, you have what you need. You have your variable for the stick. You have your variable for the string. You have how long they both are together. Okay, so use those 3 bits to solve the problem of how long is the string. Okay, give it a whirl. Give yourself some minutes to do this, maybe a minute or 2, and come on back. Okay, so if I apply what I know right now that the length of the string plus the length of the stick equals 15 meters. So I know that means I know x plus 4x equals 15 meters. Okay? Putting together equations. This is so much fun. Yeah, so we have, because the x comes from here, because that's the length of the stick. The 4x comes from there, that's the length of the string. And then 15 meters, of course, comes from here, because I need this bit of information. All right. Now, if we combine terms here, x and 4x, we could just simply say 5x equals 15 meters. Okay, and now I can only solve, because when I solve for a variable, I'm going to solve for one of these, okay, for 1x. Therefore, I need to isolate it. And to isolate that 5x, I need to divide it by 5 or multiply it by its reciprocal, which is 1/5. And if I do that, 5 over 5x equals 15 over 5 meters. Okay, because I'm dividing both sides by 5. All right, so then I end up with x equals 3 meters. Okay, and that's not my answer yet, of course, because x is actually the length of the stick. Okay, so the stick is 3 meters. All right, need to go one more step to find out what they're asking me for, which is actually the length of the string. So I know that the string is 4x. So I plug in my 3, which I've just solved for, into where the x is. So 4 times 3 equals 12. Okay? So my string is 12 meters long. Okay? And that makes sense. My string is 12 meters. My stick is 3 meters. And together they equal 15 meters. Which is quite long, I must say. Okay, so some more application to real-world problems. Okay, here we go. Example 4, expressions from word problems. It costs Margot a processing fee of $3 to rent a storage unit, plus $17 per month to keep her belongings in the unit. Her friend Carissa wants to store a box of her belongings in Margot's storage unit and tells her that she will pay her $1 towards the processing fee and $3 every month that she keeps the box in storage. Okay? So what they want you to do is want you to take that info and write an expression in standard form. Okay, and that just means combining all the like terms. Okay, if you have a number of x's, just combine them together into one x term. Okay, so write an expression in standard form that represents how much Margot will have to pay for the storage unit if Carissa contributes. Then determine how much Margot will pay if she uses the storage unit for 6 months. Okay, so first you're going to write an expression. That's this one here. We're going to write an expression first that represents how much Margot will have to pay for the storage unit if Carissa contributes. Then you're going to determine, so you're going to evaluate that expression, determine how much Margot will pay. So you're actually going to apply some charges. Okay. All right. So I'd like you to try to again give that a whirl. I think this could take some time, but I'd like you to give it a whirl and try it out. Again, we've done things similar to this at the end of Module 2. Hopefully some of that will come just rushing back to memory. Okay, give it a try, and again, if you don't quite understand it or quite get it, just do your best and then come on back and we'll work it together. Okay, so yeah, whatever you have, let's just go ahead and have you compare that to what I came up with. And this first step actually might have been maybe one of the most difficult parts for you to come up with, was writing that, just the original expression. Okay, this is not the expression in standard form as they had asked for, because we need to change that, combine, and you'll see what we need to do. But anyway, the way I came up with this is that I just took what all of Margot's costs, okay, which were here, $17 per month. That became my 17M. I just took M to be the number of months. You might have done the same. You could have used X, could have used whatever, okay? And I added the $3, okay, which was that one-time fee, that processing fee, okay? With the 17M, when you have that variable, you can tell that it can change, okay, because number of months can be different and will vary, all right? But by having this 3 just sitting here by itself, you know that it's a one-time charge. It's not going to be, you're not going to multiply that by anything, okay? It's going to stay just 3, all right? And now what I did is I went ahead and then I subtracted away, okay? I just put my subtraction sign here because I'm going to actually subtract away what Carissa is going to actually give her to use her unit. Okay, to use her unit, she said she would pay her $3 every month. Okay, and that is this one right here, the $3, 3M, 3 months, 3 per month, and then she was actually going to give her $1. She was going to contribute $1 toward the processing fee. Okay, and that was this over here was this +1. Okay. So this whole thing is going to be subtracted away. This whole bit is going to be subtracted away. Okay. So if we just go ahead and subtraction as adding the opposite, and we went ahead and did that, it would look like this: 17M plus 3 plus, okay, the opposite of 3M plus 1. Okay, which would continue as 17M plus 3 plus negative 3m plus negative 1. Okay? And yeah, that's fine. So now we have our separate terms. Okay? And then if we combine those terms, we have 17m plus, actually I don't need to do this here. 17m plus negative 3m, okay, because I am just commuting, moving my negative 3m over to be near my 17m, plus 3, that's my $3 there, plus a negative 1, okay. So you see where all of those came from, okay, and because I'm just going to combine like terms here. So if I combine my 17m with my negative 3m, I end up with 14m. And then if I combine my positive 3 with my negative 1, I end up with 2. So 14m plus 2 is the expression in standard form that represents how much Margot will have to pay for the storage unit if Carissa contributes. Okay, if Carissa contributes, that's the equation, or not the equation necessarily, but the expression she can apply to find out how much she will have to pay. All right, because of that 17, you can see it right here, because of that original $17 a month, she's only paying 14, of course, because, you know, Carissa has agreed to pay 3 of those dollars. And the original processing fee of $3 is down to 2 because Carissa has agreed to pay $1, okay, for $1 for that processing fee. All right? Okay, so that's step 1. That was the expression part. Now we are going to determine how much, the second part of the problem was here, determine how much Margot will pay if she uses the storage unit for 6 months. Okay, so now we'll go ahead and plug that 6 in, because that 6 right here is going to, of course, be substituted for every, oopsie daisy, don't do that, for every m, okay, because my m stood for my number of months, and the 6 is what I'm going to plug in, and I only need to plug it in right down here to this very simple expression, and you've probably done this already, so I'm not even going to go away. I'm just going to do it right here. And we'll just solve it right here. 14 times 6 plus 2. Okay, so 14 times 6 is 84. Plus another 2 equals 86. So, $86 is what Margot will pay towards the storage unit rental for 6 months of use, which, if that really existed, is a major, major bargain, okay, unless this thing is the size of a shoebox, all right? Yeah, that is not realistic at all. But anyway, maybe it is somewhere, surely not around here. Anyway, so that's how we do that. You could see just the wonders, absolute wonders of creating an expression and then being able to apply, substitute, plug in information that you have, okay? If we had 12 months, if she wanted to project, and this is good because if you're able to project, to see ahead about how much something is going to cost you, you can better then maybe, you know, you understand how much money you need to earn. You could ask your mom and dad for some more chores, you know, again, applying it to your young life. Maybe, and in this case, maybe Margot wants to do another shift at work so she can pay for this storage unit. Alrighty. Anywho, yeah, let's go ahead and let's finish this thing up with example 5. Okay, so now we are going to extend this idea of the inverse into division. Now we've been working with you know, converting differences into sums using opposites like we have, and the reason we have been converting differences into sums, you know, for example, all of this that we've been doing here. Remember, we have been you know, turning turning any difference like we had right here into a series of sums, right? Everything's a sum, okay? We've been doing that because, as you remember, and you probably recall, many of you, we can't apply the associative and the commutative property to subtraction, okay? So we then convert everything into addition, okay, where we could apply that. And that works exactly the same here in multiplication, okay? Division is not associative, it's not commutative, but multiplication is. So therefore, we're going to convert division into multiplication. And the way we do that, and many of you know, okay, is we take the reciprocal, okay. We take the reciprocal of the number we are dividing by, and we can go ahead and therefore multiply. I think we just did that quite recently, and like I had said, anything at all. So if you had 6 divided by 3, we could change that into a multiplication problem by 6 times 1/3. Okay, 6 times 1/3, and these are going to be the same thing. So 6 over 6 times 1 over 3, boom, boom, 1, 2, 2, 2, 2, 2, 2, 6. That equals 2. 6 over 1, I'm sorry, 6 over 1, and that equals 2 over 1, which equals 2. Okay, so same thing. The difference here, I mean, one thing you have to remember, though, a little thing you can fall into, is you can't do it this way. You can't take the reciprocal of that first number, okay, and then multiply by 3. It's not going to give you the same answer, because in this case, you'll see you'll get 3 over 6, which you'll get 1/2. Okay, doesn't work that way. So very, very, oopsie daisy, didn't mean to do that. Oops. Very, very important is that you are taking the reciprocal of that second value, or the divisor. Okay, very, very important. But anyway, yeah, we're going to extend the use of the inverse to division. Okay, and let me go ahead and read here. It's probably most of what I just said is going to be here. But multiplicative inverses have a product of 1. Okay, which was like this. So 6, and its multiplicative inverse is 1/6. And if I multiply those together, they equal 6 over 6, which equals 1. Okay, multiplicative inverses. Now remember, additive inverses were 2 plus -2, and they're going to equal 0. So when you have an additive inverse, it's equals 0. When you have a multiplicative inverse, the product is going to be 1. Okay, get rid of all that. All right, so there we go. So multiplicative inverses have a product of 1. So now what they want you to do is to find the multiplicative inverses of the terms in the first column. Okay, show that the given number and its multiplicative inverse have a product of 1. Okay, then use the inverse to write each corresponding expression in standard form. Okay, the first row is completed for you, so let's go ahead and look at it. We're given 3. Our multiplicative inverse is 1/3. That's the reciprocal. Okay, proof show that their product is 1. 3 times 1/3 is 3 over 1 times 1 over 3. 3 over 3 equals 1. Okay? Use each inverse to write its corresponding expression below in standard form. Okay? So let's see, 12 divided by 3. I'm not sure where are they getting that 12. Use each inverse. Oh, I guess they're giving you this. Oh, okay. Oh, I see. They're giving you this, and then you have to do this and this. Okay. Anyway, let's go ahead and do 5 together, and then I'll have you do the others, which get a little bit more complicated, of course, as you go down. All right. So 5, of course, its multiplicative inverse, or its reciprocal, is 1/5. Proof. All right, what do we have? 5 times 1/5 is the same as 5 over 1 times 1 over 5, which equals 5 over 5, which equals 1. Okay? just like that. Just do it like that. Now we have 65 divided by 5. So what you're going to do is you're just going to change that, like we did up here, from a division problem to a multiplication problem. So then you're going to multiply 65 times 1 over 5, okay, which is 65 over 1 times 1 over 5. And if we do our cross multiplication, we end up with 13. Cross cancellation, to 13. Okay. Yeah. So why don't you go ahead and do the rest. You see they vary in their what they look like. So when you come back, we will check them all. I'm sure you'll do well on a few of those, but you may find a little hiccup, a little hurdle on others. So just come on back, and I will help you solve them all. Whew, okay, so that was probably quite a bit of work for some of you, but hopefully you did well, and maybe you surprised yourself and did a lot better than you thought you did. By applying rules, that's all it takes. Applying rules, applying what you know, keeping it simple. Okay, keeping it simple. All right, so let's see, we did the 5. Okay, so we started here, -2. Again, be careful now. It's a -2. It's going to stay negative because we don't change anything when we're finding the inverse of a number in terms of multiplication. The multiplicative inverse is very different, of course, and it just has to do with a numerator, denominator, and how they're positioned. So it's going to be -1/2 was the multiplicative inverse there, and I went ahead and just multiplied -2 over 1 times -1/2. Interesting, and you got to remember, negative times a negative is a positive. Okay, and that's 1, and that's why multiplicative inverses they equal 1. The product of multiplicative inverses are always going to be 1. Okay, so if I applied that here to 18 divided by -2, which is the same as 18 times a -1/2, 18 over 1 times -1 over 2 equals -18 over 2, okay, straight across multiplication, which equals -9. Okay, -9. That's that answer. -3/5 offered a different look. Okay, it's no longer a single, an integer. No integer. Now it's actually a fraction. Okay. Again, it stays negative because we're talking multiplicative. All right. But it's now -5 over 3. Okay, it's reciprocal. And then if we do, -5 over 3 times -3 over 5, we get a positive 15 over 15, which equals 1. Okay, and if I apply that to 6 divided by -3/5 is the same as, equivalent to 6 times -5 over 3, it's reciprocal, okay, which equals 6 over 1, all right, times -5 over 3. I did a little cross-canceling, and I got 10 over 1, or 10 is my answer. Okay? An even different look was this one, x. What the heck could be the inverse of x? Well, x has an inverse, a multiplicative inverse, which happens to be 1 over x. Okay? Yeah, very simple. I mean, it could be when it was 5, the multiplicative inverse of it was 1 over 5. Okay? Therefore, that is going to hold true with x as well. All right? And then if we did the proof over here, x over 1 times 1 over x, it's reciprocal, equals x over x. And x over x actually equals 1, because anything over itself is going to equal 1. Okay? Y over y, z over z, 2x over 2x, 5 over 5, 9 over 9, all equal to 1. If I go ahead and apply that over here, I have 5x divided by x, which is the same as 5x times the reciprocal of x, which is 1 over x. And then I have 5, very careful putting these together because they're, I've made this mistake myself in the past. When I changed 5x into a fractional representation, sometimes kids will do this, okay, but that's not 5x, okay. 5x as a fraction is just 5x over 1, okay, right here, like anything is. Like 6 is 6 over 1. They're the same. They're equivalent, okay? So 5x is equivalent to 5x over 1, because anything over 1 does not change its value whatsoever, okay? So there we go. We have 5x over 1 times 1 over x. And if you did a little cross cancellation here, you could cancel out both x's, okay? And then you have just 5 times 1 is 5. 1 times 1 is 1, and therefore our answer is 5. Okay? And again, an even different look here. We have 2 x's. The inverse, multiplicative inverse of 2x is, of course, 1 over 2x. I think you're getting the idea now. Any whole number or whole variable is all you need to do is put a 1 over it in a fraction form to get its reciprocal or its multiplicative inverse. And again, if I multiply that, remember 2x over 1 is 2x times 1 over 2x is 2x over 2x, which is 1. Okay? Applying that to this problem here, 12x divided by 2x is going to be the same as 12x times 1/2 x. Again, if I do that, I have my 12x over 1 times my 1 over 2x. A little cross cancellation here makes that 6 and this 1. Okay, and then I have 6 over 1 equals 6. Okay, what I would recommend if you want, you might feel like you need some more practice with these. Have your mom or your dad or whomever you're working with create some sheets like this one, and all they have to do is just put some, use some integer, positive and negative integers, a couple of fractions, use some variable representations, and create a chart like this or a table like this, and have you work it out. Okay, a little practice. Practice makes perfect. Okay, well, we're going to end this this lesson here not with. Hold on, I thought I had put. Oh yes, you do have in your packets. You have a couple of sprints. Okay, a couple of sprints for generating equivalent expressions. All right, and we have a round 1 and a round 2. So if you will go ahead and find that right now, that's at the back of lesson 2. It's actually right. It looks like it's at the very end. It's after all the exit ticket and the problem sets. Okay, there's a generating equivalent expressions round 1, and then a generating equivalent expressions round 2. And if you want to, after we do this lesson summary, you can do a sprint. I will do the 1-minute timing thing. All of these answers to these sprints will be found in the binder answer section of the website. So you can go there and get the answers, and you can check. And again, these are 1-minute rounds. This is not real. This is going to be kind of laborious at first. You're going to just kind of drag on through it because they are expressions now, and not just plain simple multiplication facts. But yeah, give it a whirl. So after we do this lesson summary, I'll go ahead and take a few minutes for those of you who would like to do some sprints. Okay, so lesson summary here just says, rewrite subtraction as adding the opposite before using any order, any grouping. Okay, this idea of any order Any grouping, again, is commutative and associative properties. All right, so you're always going to rewrite subtraction into addition, okay? And then you're going to rewrite, in the same fashion, rewrite division as multiplying by the reciprocal before using any kind of associative or commutative property. Okay, rewrite division as multiplying. The opposite of a sum is the sum of its opposites, and that was that whole idea when you're talking about changing subtraction into addition. You would do that. And then division is equivalent to multiplying by the reciprocal, which is what we just finished. Okay? Yes. Lots of material. Truly hope not everyone is overwhelmed. I know a few people will be. If you need to break these lessons up into a few different lessons, a few different days, please do that. I don't want anybody rushing and not fully understanding this material. Okay, for those of you who stood for the sprint, again, this is at the back of lesson 2, generating equivalent expressions, round 1. Okay, this is for, again, lesson 2, round 1. And when I say ready, set, go, I'll give you 1 minute. The timer will sound, and then you can stop. You can go and go to the binder answer sections and see how many you got right, if you'd like to now, or you could just wait and do round 2 and see how many you get right after that, okay? Just a way to practice. All right, so here we go. If you're ready, get your pencil ready. On your mark, get set, go. Thirty seconds left. $15 seconds. 5 seconds. 2, 1, and 0. Okay, there you go. Go ahead and add up your actually just circle the last one you did, and then you can go ahead and check those later. But why don't you go ahead and get ready? We can do well, if you want to pause right now, you can go ahead and check your answers. Come back and do round 2. Okay, so go ahead and flip over. You have your round 2 sheet. Okay, generating equivalent expressions round 2. And when you're ready, here, get your pencil ready. On your mark, get set, go. $15 seconds. 5 seconds. 3, 2, 1, 0. Okay, so go ahead now and you can check those answers at the binder answer section. And hopefully you made some improvement. It'd be good to do this occasionally just to give yourself give yourself some practice. Okay? Well, again, like I said, I hope this wasn't too difficult. I hope you enjoyed it, some of you, most of you. All right, and I'll see you in the next lesson.